Thank you very much. The microphone is working. It's a nice technical setup you have here. Hey, Niels, how are you doing? I'm a bit nervous. I have Mario over here, which is a problem. No heckling in the middle of the presentation. A challenge, yeah, it's not a problem. Well, like Martin said, I will talk today about automatic malware detection in high-speed backbone networks. But before that, I want to give a brief background about myself and about the company and what we're doing. I promise 3 slides, and then I won't talk about variant products anymore, okay? Starting with myself. Like Martin said, I'm the head of product management for Variant Cybersecurity Unit. Before that, this is an old version of my presentation. I must have made a mistake copying it. But never mind. I was the founder of Cyber Security Solutions, which is missing from the title over here. And we dealt with the development of network analysis systems for finding malware. At the same time, I was doing strategy work, strategic consulting for organizations, governmental and government and corporate, usually in the area of the defining and building of security operation centers. Before that, I was director of cybersecurity for the Israeli government, and I think that's enough of background. And if you want to talk about that later on, I'll be happy to. The most important thing that I'm the father of Noah and Maya, and this is not a stock photo. So I'm happy about that. Yeah. Variant Cybersecurity Unit deals with 2 types of customers. We deal mainly with national certs and CSOCs, or cybersecurity operation centers, and we deal with large government and military organizations. We also cater to several large-scale enterprises, but these are the main areas of interest for us, and these are the main, the customers that we work with, also with Variant for a long time now. And what we do is mainly network security solutions, and I'll talk a bit about this field in this presentation, and training, consulting, and intelligence services. If you haven't been to our booth, it's downstairs at the 2nd floor. We'd be happy to talk to you about everything that we do. I will have 1 slide that has some connection to our products, but other than that, I'm going to talk on a general concept. So, speaking about automated malware analysis in high-speed networks, let's start to analyze that concept. So, I'm guessing everybody here knows what an APT is, right? Anybody? Any person that doesn't know what an APT is, please raise your hand. No courageous people. Okay, wonderful. Well, in the last 3, 4, 5, 10 years, depending on how you place the history of cyber conflict, we've seen these new attacks cropping up. And having them crop up meant that we've seen more and more attacks, mainly getting more media attention. And we've started to see the fact that legacy security systems were not up to par in the detection and mitigation of these attacks. So in the last 3 years, we've been hearing more and more buzzwords about new technology that has been out there. Maybe it's old technology that is being used now, but maybe it's new technology that is cropping up. We've heard buzzwords like sandboxes and anomaly detection and stuff like that. And what I'm going to try and do in the process of this presentation is talk about the different technology that is out there, both the legacy and the new technology. Try to understand the pros and cons of each of the technologies. It's going to be a very high level, very quick run through the technologies. And then in the end, talk a bit about the challenges in high-speed networks. And when I talk about high-speed networks, I'm talking about networks which are above 100 gigabit per second. Anything lower than that is interesting, but not interesting enough. So the process of automated malware detection is usually divided into 3. And I actually have a nice laser that they gave me here, so I will use it. We're talking about acquisition, analysis, and investigation. Now, acquisition and analysis usually happen in the same box. You have a box that does acquisition of traffic of the network, and then it does analysis of traffic of the network. But then you have all of the analysts coming in and doing investigation. They're doing network forensics, they're doing endpoint forensics, they're doing reverse engineering on Trojans, they're doing log correlation in SIMs. They're doing a lot of stuff over there. So in this presentation, I will not talk about investigation because it's a large project, a large subject, and I don't have the time to get into all of the aspects over there. But I will talk about acquisition and analysis. Diving a bit deeper on this, and I'm sorry, starting to do this, when me and my colleagues in Variant have started to build this presentation, we said, okay, what is this playing field? And we started building this map of the playing field. And basically, let me stand over here so I can see it as well. 1 second. So in the acquisition layer, we have 2 internal layers. We have the physical acquisition layer, where we actually put stuff in the network that are supposed to tap into the traffic. And then we have a software that uses the acquisition layer or the physical acquisition in order to get information out of the analysis engines. And then in the analysis engines, we also have 2 layers. We have an initial work that is being done on the traffic. And then we have different types of analysis engines, whether they are signature-based or behavioral-based. And I'll talk about these, not specifically signature-based in these, but I won't talk about these because these, happen to be there and their basic software being done for years now. So starting with acquisition. And I have 1 slide about the physical connection, and then I'll move on to talk about the software powering this. When we talk about putting things inline or in a proxy version, or when we talk about tapping or mirroring, for me it's important to emphasize that there is no school solution for this. There is no one way which is the best and the other ways are wrong. Actually, it's true for my entire presentation. There is no one technology which is the best. We need to understand what are the needs on the architecture of our product and of the analysis that we want to do. And the different needs and architecture drive to different acquisition or physical acquisition methods in this place. I'm sorry for the cameraman. I like to move around on that. Sorry. Yeah. So when we want to do man-in-the-middle attacks on the traffic and do SSL man-in-the-middle and decrypt the data, or when we want to do challenge response and be more active in our defenses, then we need to be inline or have a proxy. The problem with this technology is that usually when we're inline, we have 0 tolerance for latency. Not because us security guys, we have no problem with the network being slower, but the IT guys don't really like it, and the users don't really like it. And usually then we get kicked off the network. So products that actually do this kind of thing need to be very fast and need to be very streamlined. Tapping is more seamless. It's easier to do tapping. You have to shut down the network once, and then you can get all of the data that you want. It's usually invisible to the user afterwards. But the fact is that you do need to shut down the network once, and in ISPs, that's a problem, especially in ISPs that have few links to the internet and can't roll over to other links in the process. And you may need dedicated hardware with high availability because, again, if you tamper with the network will tamper with you, or in Soviet Russia. And mirroring is probably the quickest and most efficient and cheapest way to actually, by the way, if you're using Cisco, it's mirroring. If you other guys, it's span porting. I'm mainly a Cisco user in my past, so I say mirroring. It's quick. You put your network in, you say mirror all traffic from here to there, give me both sides, and you go on with your life. The problem is that usually routers and switches CPUs, when they start getting high demands, they drop the mirroring and span ports. They have to be very successful in moving packets from one side to the other, and this mirroring thing is interfering with their work. So they will drop it. And we've seen attacks dedicated to raising the CPUs of switches and routers to drop the mirroring and then do intelligent attacks that the analysis engines won't find. Sorry. So moving on to the software that powers that. The easiest way to do analysis on a network is to do direct work. And you do it either via using a network processor or by using one of the capture libraries. libpcap is probably the most famous one, but there are other more efficient ones like pfring and others. The benefit here is you don't need any storage. You can do it directly. You get results quickly. The problem is you don't have any stored data, which is a problem because you might want to take a look backwards a bit and get some more data what happened in the past. You need a very large memory footprint. If you're doing stuff in real time, you need the memory in order to do the analysis. And no, that went out in the final version, sorry. The last one. NetFlow or IPFix, there are a lot of NetFlow enthusiasts out there. I mean, I think that CERT Carnegie Mellon, CERT-CC, is one of the biggest advocates for NetFlow analysis and the entire Hadoop community with them. It has benefits. You don't need a lot of storage. It has very low performance requirements. And you can actually get NetFlow data from the entire network. from the entire network, for all of the nodes, from all of the routers, all of the switches, sometimes from all of the computers, and place them in one place and then ask intelligent questions. The problem is you get 5 tuple. And that's it. So the amount of work you can do on NetFlow is limited to the data that you receive from the NetFlow traffic. Which moves us on to full packet capture. Full packet capture shouldn't be here. It's analysis combined with acquisition. It usually ends with full packet capture. It doesn't move it to any other place. But it's still here. It provides great detail. You can do a lot of work on full packet capture. You can go back in time. You can find stuff that happened in the past. But you need huge data stores in order to do this in fast networks. And when I say huge, I'm talking about huge. We've done some sizing on this. And then, you know, if you have anything under 10 petabytes, you're in a problem. And then you have to actually ask questions about these 10 petabytes, which is also a problem. And it's time and resource consuming. You have all of this data. Now what you do with it? You need the analyst to sit down and take the post-mortem approach and research and actually get to stuff with it. The last thing I'm going to talk about in acquisition is DPI. DPI is probably a mix between NetFlow and full packet capture. It gives you the ability to do layer 7 metadata comparison, get into the traffic, get more detail on what's happening, and decide if you want to capture this traffic or you want to send this traffic to an analysis engine. The problem here is the DPI costs a lot of CPU and costs a lot of computational power. And in order to do this right, you need dedicated hardware, and hardware that usually costs a lot of money. So, moving on to the analysis phase, and I'm trying to be on time. So, yeah. Moving on to the analysis phase, I want to talk about, you know, like I said, there is the analysis platforms which I won't talk about, which have pros and cons, but everything is done. They are all done in the process between metadata extraction and stream analysis, which is reconstruction of the traffic, and file extraction. But I will talk about the signature-based and behavioral analysis and the different aspects of behavioral analysis. Oh, here I will need the laser. Let's start with signature-based. We're in the technical track. Who here has an IDS? Raise of hands. 1, 2, 3. No, not too many people, but okay. No. Signature-based, probably the oldest technology in the book. I've been doing it for years now. I think the Snort project is up for 20 years almost, approximately. I've been doing a lot of good job in signature analysis. I mean, the other type of signature analysis, which is not IDS, is called antivirus software, which is also a legacy software. The best analysis engine if you know what you're looking for. If you have the signature for something, then you'll get the least false positives, and you can do almost everything on the traffic, on the endpoint, wherever you sit. The problem is, if you don't know what you're looking for, you don't have the signature for the traffic, you probably won't find it. And from my personal experience, you know, being in charge of the Israeli government ISP and running some IDSs in my life, you build a signature, you get a lot of false positives, then you tweak it, and you get a lot of false negatives, then you tweak it back, and you get a lot of false positives, and you run this until the signature is okay, and then the threat changes, and the signature is not good anymore. So you have to do a lot of work on signature tweaking and signature development. Sandboxing. Who haven't heard about FireEye? They are really driving, by the way, market-wise, and they're doing a good job, and it's good technology. Other sandboxes are out there as well, so give them a chance. What? No, sorry. Sandboxing is the new black, as Karen Azari would say. And sandboxing means that you sit down on the network, you extract all of the files, you run them on a virtual machine. By the way, some sandboxes give you the ability to run on physical machines, which is a plus in my eyes. And it's good, because you have low false positive. If somebody is actually attacking you via a zero-day exploit, and then you'll see it when it runs on the virtual machine. So you understand what's going on most of the time. And you cover unknown malware. Again, zero-day, exploits your machine, you see what happens, you get a report, you say, okay, this is a zero-day, it's new stuff. The problem is, it's a single threat vector approach. You get a file via email, you get a file via the web, and then you analyze that. But what happens with drive-by downloads? What happens with the cleaning lady? Oh, sorry. put a USB key in your computer. What happens if somebody is running some kind of code in your, it's not foolproof, and it's a problem. The second thing is modern malware, definitely APTs, are developing ways to detect virtualization and bypass sandboxes. And you can ask Charlie Miller, which is usually talking here, but not this year, which just developed a way to bypass the Google Play bouncer virtualization, which is a sandbox. Difficulty of result interpretation. I didn't say it for the signature detection because that's easy. Here it's medium because the reports you get from the sandbox are usually more obtuse than the alerts you get from an IDS, but still you understand what's going on there. Then we move on to anomaly detection. Anomaly detection, we've seen more and more anomaly detection techniques and products cropping up lately. Some companies have been doing anomaly detection for a long time. Some are new and doing interesting stuff. And Cisco just bought Cognitive Security, which is an anomaly detection company. What happens with anomaly detection is that the system sits on the network, either on NetFlow or on Stream or on something else, and does a baseline. It listens to the traffic for days, says this is the normal behavior of the network, and then if it sees an anomaly, it says, okay, this is anomalous. This part there, what happened there is anomalous. Now, benefits, it covers unknown malware. If an unknown malware is anomalous, then the system will give a report about that. And also a large threat vector coverage. I mean, if we're doing anomaly detection on HTTP, then it will be okay, good on HTTP. If we're doing anomaly detection on DNS, then we'll see DNS. If we're doing anomaly detection on NetFlow, we'll see the entire network. So we have the ability to take a look at a lot of things. The problem is there is a very high rate of false positives in anomaly detection, a very, very high rate, actually, because the internet today is anomalous. When I will post tomorrow a cat story in YouTube, and all of the people here will go and see the cat story, that's an anomaly. Because nobody here went to YouTube yesterday to see the cat story. Actually, they did. But something else. So the internet is anomalous. When you take a look at modern networks today, they are anomalous. It's very hard to baseline them. The second thing is, if there was malware activity going on when I was baselining the network, then that's normal. I won't see it. It's very hard. The last thing is it's very hard to interpret anomaly detection results. That's because it's a black box. Anomaly detection or by the way, unsupervised learning algorithms will tell you this is bad. It's red, then it's bad. But it won't tell you it's bad because it's red. It'll just tell you, go there, that's not good. And it's very hard to understand what they want from you in the end. Moving on to my favorite topic. I've been developing these products for 4 years now, so I like supervised or semi-supervised learning. By the way, just to put things in context, supervised learning is when you learn on what's good and what's bad. You give good examples and bad examples, and then you apply that to the traffic. Semi-supervised is that you give either good examples or bad examples, and then you try to learn on that. Again, here the benefits are that you cover unknown malware. I learn from bad malware, samples of bad malware, and I generalize these samples into a greater context, I can find malware that I don't know about. But the drawbacks is that you get a relatively high false positives. And when I talk relatively high, you get less false positives in anomaly detection and more false positives in sandboxes, to put you in the place. And you have to do a lot of work, product-wise, by the way, in order to fight these false positives. And it's high with an asterisk here because depending on the algorithm that you use, it can be medium, it can be very high. So decision trees, it's very easy to understand what happened, why this is bad. On the other hand, SVMs are a bit harder, and decision forests are something you can't get any understanding from because you don't get the specific route that something got. So it's a problem. Now, this I've asked for authorization to talk about this slide. I got it this morning. This is, as of today, a patent application that we've done. and to talk a bit about the problems that we have in semi-supervised learning. So what we do exactly, we look for command control channels in HTTP traffic, and we try to generalize on bad stuff that we found in the client network. And what we found is that although you have very good examples, when you get into a network, you get a lot of good traffic, but you don't get enough bad traffic to learn on. So this is an example of how we deal with things to all of you academics out there, just to give an idea, okay? So what we do, we have an infected network back home. I'm hoping that the IT guys don't know this, but maybe they do. And we run malware on this infected network. Thousands of malware specimens that we've downloaded in a torrent from the enterprise network, but never mind that. And then we have blacklists that we've tweaked ourselves and we've worked on in the last few years. And we run them through some kind of data extraction, statistical aggregation, not relevant for this specific presentation. But then we have a list of bad records. Malware, which is sitting, in our networks. But then we go to a client site or a POC site or any other site that we go to with our system. We do the same data extraction, but we use the blacklist that we've compiled back home. And we have two types. I'm missing my laser. 1 second. We have two types of records. We have bad records and we have unknown records. Unknown records can be good, they can be bad, we don't know yet. But we use the data in these bad records in order to give more learning material for the learning algorithms, to enforce the learning algorithms. Now, we know that when sitting on a client network, these do not look the same. There are differences in traffic between this network and that network. But what we've found in time is that although good records between networks are determinately different, bad records tend to stay in the same statistical area, more or less. So we push that to learning algorithms, and then it goes and has confidence levels, and there's a threshold, and we move on to the analysis phase, and here a person sits down and says, this is good, this is bad, this is good, this is bad, this I don't know. This I don't know goes to host, detailed analysis, like I've said, endpoint forensics, network forensics, doesn't really matter. But the thing is, in semi-supervised learning, that we can rebuild the models. So if I have something good here, or something bad here, I can go and tell the learning algorithm, look, this is bad. And tomorrow I want the learning algorithm to take into consideration that this is bad. No, just an example. So I have 7 minutes left. And I want to give 3 slides about high-speed networks. Variant, as a company, has dealt with high-speed networks in the past, a lot of high-speed networks. We have DPI capabilities besides our cyber area. And this is some insights that we've seen. I'll talk about the problems, and then I'll talk about how we tend to handle these problems. So the problems are mainly performance and scalability. When you're dealing with networks above 100 gigabit per second, you need performance and scalability. And the fact that usually, when you take a look at these networks, they're not one pipe that does 100 gigabit per second. Usually, they're distributed networks. They belong to ISPs, right, Niels? And you have to deal with stuff over there which you don't deal when you have one gateway to the internet. So when we talk about performance and scalability, probably the best thing, the worst thing that we have to deal with is throughput handling. We have to deal with a lot of data, which is coming very fast at us. So we need to handle that. We need to analyze that. We need to do acquisition, then we need to do analysis. So we start with either using dedicated hardware, big machines that can do hundreds of gigabit per second of acquisition of the network, but these costs a lot of money. Or we can do distributed computing. Get a lot of computers, pipe it through to different computers, and then run the analysis there. But then we need our software to work from the scratch in distributed computing, because if we don't program it to work in distributed computing, it won't really work. The second thing is our analysis bottlenecks. Analysis bottlenecks is the fact that maybe I can do acquisition in hundreds of gigabits per second, but usually my Intel CPUs behind that can't handle that load. They have a lot of problem in handling 100, 200, 300 gigabits per second. So here I can do either scale out, one acquisition, a lot of analysis things. I can do application-based filtering. My advanced detection system does command control detection on HTTP. So let's pipe only the HTTP to that analysis engine. And let's pipe only SMTP or FTP to the sandboxes. And we need to streamline the analysis process. When we're working in high speeds, we need the analysis engines to be written properly and fast. And I'm sorry, Microsoft people, usually not in a Windows environment, just because the libraries for the network cards are much better in Unix. The last thing are low probability events. Low probability events is exactly what they seem like, the things that happen rarely and can throw a monkey wrench at your analysis process. The thing is, when you get a lot of traffic, low probability events become high probability events because they will happen in the end. And here you have to understand the network you're sitting in. You have to understand what kind of low probability events you're going to see. So you need to be very integrated into the network. And from time to time, you need the ability to go to the machine, change signatures, change algorithms, understand that you've seen a low probability event and that you need to handle this in the future. Last slide before the question slide. Distributed network topology, these are not problems, these are solutions. In distributed network topology, we do two things. We do either link aggregation, which in turn means that we need to have stronger network equipment that will handle the link aggregation, handle the duplication of traffic, and then send it to a central aggregation place. And again, all of the problems that we've seen previously. And we have a problem of asymmetric network monitoring. In ISPs, when you monitor traffic on a national level, sometimes a GET request goes to a specific link, but the reply comes through another link. And if you want both sides of the traffic, you need the ability either to do central aggregation and do analysis of everything in one place, or to do some kind of correlation back in the back end of your equipment and say, this traffic, this GET request belongs to that response, and let's mesh them together and do analysis on top of that. So I've tried in the last 30 minutes to give a brief technology overview. I hope it was successful. If you have any questions, I'll be happy to answer. Yeah.
I have a question. When and how you think is a good moment that a set of bad examples is good for a new signature?
Well, it depends.
Because each bad example is an instance, while a signature is a class. So question, how you can, from the set of instances, create a new class?
Well, it depends on the scale and scope, as everything in life. In the end, one instance can be a class of its own. It can be. And I'm not a big advocate. I've tried to stay objective in this presentation. I'm not a big advocate of signature-based detection anymore. So behavior is one thing, and behavioral analysis is one thing. But when you start working signature-based and you see enough stuff, then in the end you get some kind of generalization. But I've seen IDS signatures which are generalized, and I've seen IDS signatures which are dedicated to a single packet that you know is coming to be a bad thing. So it depends on how detailed you want to go in your signatures. And more signatures mean more load on the CPUs and the more memory footprint for the IDSs. But it really depends on the architecture you're running and the detailed level of the signatures that you want to build.
But I understand your learning algorithm, which is built for into your system, in some sense is moving from bad examples, instances, to some kind of more general classification of. So there is some elements of, generalization or classification. So towards signature.
I know. So here, maybe I'm trying to be more general in concept. I don't want to talk specifically about our product, but in supervised or semi-supervised learning, we're not talking about signatures at all. The other way around, we're talking about statistical analysis and general concepts of how behavior looks like. What happens is that you take malware data, you say in that malware data, you say this is Zeus, this is Configure, this is Stuxnet, this is another group, and you learn from these elements. You have, in the end, you have a lot of indicators. You have, let's say, if you have 100 features, learning features, and you have 100 axes in space, and you put a point, and you say, in this point there is something I know which is bad, and then you create a sphere around that point. And you say everything around that point in a 100-axis environment can also be bad. So you play with the radius. The closer it is to the point, the more it is that malware that you've learned from. But as it grows, it becomes less and less the malware that you learned from and more generalized. Now, the game here is to do two things. The game here is to know where to put the thresholds, so the generalization will give enough bad things and not too many false positives. And the second thing is to do the generalization in a way that will cover most of the malware that you will see in the network, or at least most of the interesting malware that you see in the network. But it will not create a signature. It will create a list or a threshold in learning algorithms that will be able to decide in the end. And it's a type of a black box. Say bad, good, bad, good, bad, good, bad, good. Bad level 7 or bad level 9 or bad level 10, which is probably the same malware that you've learned from.
More?
Lieutenant Colonel Katı from Turkish Army Cyber Defense Branch. Instead of asking question, I will add one comment. In case the traffic is encrypted, all the approaches that you explained are not valid. When the traffic is encrypted, in the high bandwidth networks, we cannot do anything.
It's true for signature-based analysis. It's true for sandboxing. It's not true for behavioral analysis. Neither unsupervised and semi-unsupervised learning can work on encrypted traffic just as well as they work on unencrypted traffic. You don't look at the data itself. What you look for are characteristics of the traffic. So companies have been doing anomaly detection, which is unsupervised learning, for years on encrypted data, and they found, this is normal encrypted data, this is abnormal encrypted data. So
yeah, but you can reach some kind of result, but false positives or false negatives will be high on it.
That's the gold bullet is to find the capability to manage those. If there's nothing else.
Any other quick, urgent? Otherwise, we might have Asaf also in the
Thank you very much.
panel. Okay.